that I thought you guys might find interesting. So yeah, this basic question, can we know the shape of space? Where when I say shape, I really mean topology, if you know what I mean. I'll explain that a little bit as we get going. So one reason I think this is like a nice philosophical question is because there's this big question, like, what are the limits of science? Can science tell us everything about the world, or are there things that are, for one reason or another, inaccessible to science? So I think in the 19th century, probably, let me put it this way, I think the 19th century was sort of like the peak of optimism about the possible limitlessness of science. So here's a nice quote from Charles Saunders Peirce, who was an important 19th century American philosopher, but also by profession a physicist. So in the period when he wrote this, he worked for the US Coast and Geodetic Survey. So essentially, he made his living by making precision measurements of gravity until he lost his job. He tended to lose jobs, so he lost that one eventually. Anyway, he wrote this while he was on his way to an international congress about units of measurement, which, as you probably know, was a hot topic in the 19th century in a way that it isn't anymore. So here's his thought about what makes the scientific method so amazing. He says, on the other hand, he's just said something else, all the followers of science are fully persuaded that the processes of investigation, if only pushed far enough, will give one certain solutions to every question to which they can be applied. Different minds may set out with the most antagonistic views, but the progress of investigation carries them by a force outside of themselves to one and the same conclusion. This activity of thought by which we are carried, not where we wish, but to a foreordained goal, is like the operation of destiny. No modification of the point of view taken, no selection of other facts for study, no natural bent of mind even, can enable a man to escape the predestinate opinion. Okay, so he has the view here that the scientific method has this feature, it's sort of like super objective. Two people could start out with quite different sort of background knowledge and beliefs about the world, but as long as they both were applying the scientific method and they both were pursuing the same question, if they collected enough evidence, their opinions would converge to the truth about any question whatsoever. It's hard to tell how widespread this view is now, I'd say. I think probably most philosophers, sort of for reasons that we'll be reviewing tonight, are dubious that it's true. On the other hand, many working scientists, physicists especially, Nobel Prize winners especially, in their popular writings, will often say something like, well, of course, if we ever meet extraterrestrials, their science will be exactly the same as ours. And I mean, it seems like they think that at least for some scientific questions, like maybe what are the laws of nature, you know, as long as you're sufficiently intelligent and you've had enough time, you will reach the correct answer eventually, which is, I think, quite similar to Peirce's view. Although Peirce's view isn't restricted just to the laws of nature, it's about every fact we might investigate. So tonight I want to talk about a fact that we're interested in and we investigate, but it appears is beyond the reach of the methods of science. Okay, so the shape of space. So let's start out with the nice, easy to visualize and quite straightforward, relatively straightforward, two-dimensional case. So obviously we're interested in the three spatial dimensions, but let's start with two spatial dimensions because it's sort of easy to get a grip on what's going on there. So, you know, think about the way the simplest kind of video games work, where you drive your tank off the left end of the screen and it just comes back on the right end of the screen at the same, you know, the same height along the screen, and the same for the top and the bottom. If you think about what's going on there, I mean, the screen is a square, but the points on the top side are identified with points on the bottom side, and points on the left side are identified with points on the right side. And so you can think of it as folded up into a torus, the surface of a donut. Now, in Euclidean space, the surface of a donut isn't flat like the square is. I mean, I guess I'll say more about what I mean about that in a second. So we're sort of imagining something that can't actually be embedded in three-dimensional space, but that's fine. We're thinking like mathematicians, so we don't care. So that's the torus. Another closely related surface, the Klein bottle. Okay, so with the Klein bottle, what are we doing here? We're, let me make sure I don't just say it all backwards. Yeah, so we're still identifying the left and the right in the same way we did with the torus, but now with the top and the bottom, we're identifying them with a twist. So if you go off the top, you come back up the bottom, but you've been reflected. So, the spaceship has its orientation reversed when it travels around. Okay, so those are like two nice surfaces. Here's another one, the sphere, right? The most familiar one in a way of all. Unpleasant thing about spherical geometry, every pair of points determines a straight line, which on the circle is on the sphere is a great circle like the equator. Every pair of points determines a unique straight line, except pairs of points that are opposite to one another. So like the North Pole and the South Pole, there's lots of ways to draw great circles through them, all the long lines of longitude. Right? So this is a general thing. If you have 2 points on the sphere and they're antipodal, which means they're opposite, then there's infinitely many straight lines that go through them instead of just one. There's a way of fixing that, well, without changing the geometry very much at all. So this is like something people, in the 19th century, people tended to think, this is better than spherical geometry, elliptic geometry. So here's one way to it. You take a sphere, you cut it in half, and then you identify opposite points on the equator. Okay, so you leave everything away from the equator just the way it is, but you identify opposite points on the equator. So now it's going to have this flipping orientation feature that we saw in the Klein bottle. It's going to locally, everything's going to look just like it does on the sphere. But now it has the cool feature that in the elliptic plane, any 2 points determine a unique straight line. So that's why some people think it's more awesome than spherical geometry. Okay, so now that was just quickly introducing like 4 characters that will be helpful points of reference for us. Let's say a little bit about what topology is, because I said the talk is going to be about whether or not we can determine the topology of space. So you've probably heard this before. The topological features of spaces are those that are invariant under continuous transformations, like stretching and deformation, no tearing allowed, no folding allowed. No, you can't puncture things. So like the example everybody always gives, the surface bounding a coffee cup, a physical coffee cup, and the surface bounding a physical donut are the same from the point of view of topology because you can continuously deform one into the other. They're both just the torus. But the Klein bottle, the sphere, and the elliptic plane all have a different topology from the donut. You can't continuously transform the surface of a donut into a sphere because of the hole. Okay, and similarly, you can't transform the Klein bottle into the torus or the elliptic plane into the sphere. These are 4, from the point of view of topology, they're 4 distinct things. Okay, it's easy to run 2 things together because of the way I've been presenting things, topology and geometry. So each of those 4 items came with sort of a natural geometry as well as a topology. In 2 dimensions, an awful lot of geometry is just encoded in this one number at each point of space called the curvature. So we can think of it like this. We've got a 2-dimensional thing like a torus or a sphere. At each point x, we're going to assign a number called k of x, the curvature at x. And that's basically just telling you how close the geometry comes to being Euclidean at that point. Okay, so in Euclidean geometry, every small circle obviously has area pi r squared. In a non-Euclidean two-dimensional space, every small circle has a slightly, an area that's a little bit different from pi r squared. Here's the formula, right? Pi r squared, and then you get a fourth order correction, and then you get higher order corrections. And basically, k is the coefficient of the fourth order correction. So for some spaces, k will be negative. In some spaces, k is negative everywhere. In some spaces, k is positive everywhere. In some spaces, k is 0 everywhere. And then there are other uglier spaces that mix up the cases. So we say a surface has constant curvature if k doesn't vary as you move from point to point. And the way we constructed the torus and the Klein bottle made them k equals 0 or flat spaces, because they looked just like Euclidean space geometrically as you moved around. So each of them locally looks like the Euclidean plane, and then it has a different global structure. And here, the surface of a physical donut has the topology of a torus, but its geometry is not actually k equals 0. It varies from point to point. So the torus we're sort of thinking of is one that can't be embedded in three-dimensional space, but it could be embedded in four-dimensional space. Similarly, an ordinary sphere is a surface of constant curvature, constant positive curvature. And so is the elliptic plane, because it looks just like the sphere everywhere. And spheres can be different radius. That corresponds to different values for k. Good. But just like in the torus case, like we could start out with something that had the topology of a sphere and then give it a geometry that varied from point to point, like an ellipsoid would have that feature, or a potato. Okay, we're almost done with surfaces. One last slide, I think. So we're especially interested in closed surfaces because they're neat and the mathematics of them is simple and straightforward. So they have finite extent and they don't have boundaries. So all the ones that we've been talking about, the sphere, the elliptic plane, the torus, the Klein bottle, those are all closed surfaces. Now, there's a really fundamental interaction between geometry and topology, it turns out, that if a surface is flat, if it has a constant vanishing curvature, and it's closed, then it has to have the topology of the torus or the Klein bottle. There's no other option. And similarly, if a closed surface has positive constant curvature, then it has to be topologically a sphere or an elliptic plane. No other options. So in particular, you notice there's no closed surface that could have both a flat metric and a positive constant curvature. That's impossible. If you know the topology, you know which one it is. Now, I've only mentioned those 4 examples. There are actually infinitely many other topologies a closed surface could have. I've got pictures of a couple of them at the bottom, and you can see how to go on in that series. You just keep adding handles to spheres or toruses. And then you get an infinite series of closed surfaces that can't have a flat or a positive curvature metric. Each of those ones in that series can have a metric of constant negative curvature, which we haven't talked about. And in fact, yeah, every closed surface admits a metric of constant curvature. So 2 topologies correspond to flat surfaces, 2 topologies correspond to positive curvature surfaces, and then infinitely many correspond to constant negative curvature. So good. That's the neat, easy 2-dimensional case. I'm going to say much less about the 3-dimensional case, but even though it's what we're really interested in, partly because it's far more complicated. So there's just one slide about the 3-dimensional case. So our basic notion of curvature there in the 2-dimensional case was all about circles and areas of circles, how close they came to the Euclidean formula. We're going to do the same thing in 3 dimensions. So we've got to say, now our notion of curvature is going to assign a curvature not just to a point, but also to a plane through that point. Okay, so in principle, you could have a three-dimensional space where at each point, the curvature varied as you varied the plane through the point. Of course, we're going to be interested in constant curvature ones, where the curvature doesn't vary from plane to plane at a point or from point to point. Okay, but really here, I should have written the formula so that k was a function of both x and this plane pi, and I shouldn't have used the same symbol for the plane pi as for the number pi. So the formula is kind of a mess. Okay, now one thing that's important for us is, as in the two-dimensional case, only exceptional topologies in the three-dimensional case are consistent with having a flat geometry. In fact, of the countably infinitely many closed three spaces, only 10 admit flat geometries. Okay, so just like in the two-dimensional case, it's only very exceptional topologies that are consistent with having a flat geometry. There are some disanalogies with the two-dimensional case. So in the two-dimensional case, only two topologies were consistent with constant positive curvature. In the three-dimensional case, infinitely many topologies are consistent with the constant positive curvature. Also, in the two-dimensional case, all closed surfaces admitted a metric of constant curvature. In the three-dimensional case, it's not true that all closed three spaces admit a metric of constant curvature. So it's the ones that admit flat metrics are doubly special. First of all, because they admit a metric of constant curvature at all. And then among the ones that do, only very exceptional ones admit flat ones. Whew. Okay, that's what we need to know about topology and geometry for this talk. Does anybody have questions about the stuff that's happened so far? I feel like you guys let me talk more than I expected you to so far.
Not seeing any questions on my end.
Okay, all right. So I'll keep going. Maybe this will be a very short talk. I thought it would take longer to get through this. Okay, so now I want to talk about this question we're interested in, cosmic topology, and whether or not observation ever, in principle, does observation give us enough information to decide what the topology of the universe is? Okay, so we're always, I should say, for this purposes of this talk, we're always going to think of it being possible to divide space-time up into space and time, which it is in cosmology, basically. And we're always going to think of time as having the topology of the real line. So basically, when I ask about the topology of the universe, I'm asking about what is the topology of space. Okay, so let's start with some very early observations about the problem of determining spatial topology in relativistic cosmology. It goes back, like everything does, to Einstein's paper of 1917 about cosmology. So he proposed a static universe whose spatial slices were three spheres with the ordinary round, highly symmetric spherical metric. So when I say it's static, I mean there's a way of slicing space-time up into spatial slices so that the geometry and matter content of each slice is the same. So nothing really is happening. And it's eternal towards both the past and the future. So it's not very much like our current cosmological models. But at that time, there were only hints that the universe was expanding. And so it made sense to look for a universe that wasn't expanding. If it wasn't expanding, presumably it had been like this forever. So that's what he was thinking. And he deliberately set out to find a cosmological model with those features. It turned out that there was no solution to the equations he'd written down in 1915 with those features. So he changed the equations. He changed the equations by adding this cosmological constant term, just so that this thing would be a solution to them. Now, some interesting predictions of this model. Well, Einstein, immediately after publishing this paper, like in the middle of March, like literally a few days later, he was writing to his friends saying, here's something cool about this. If space is a sphere and you know, everything's static, so light has plenty of time to travel all the way around the universe. Right? Light has infinitely long to travel around the universe, and the universe is finite in extent, so light will get everywhere. So think about, there we are on the surface of the sphere. There should be a star near the point antipodal to us. I mean, there are stars basically evenly spread out, and you know, his universe wasn't huge, but it was something like 10 to the 7th light years across. So he was thinking like, yeah, there ought to be a star pretty close to the point opposite to us on the sphere. And because, you know, a star close to us, the light would just be coming along one light ray. But the star at the antipodal point, the light would be coming towards us along all these great circles that connect us to the antipodal point. And so we should see a lot of light coming from this one star compared to other distant stars. And because, you know, the perfect spherical symmetry is only approximate, I mean, really, you know, matter deforms geometry and general relativity. And so there are these stars everywhere that are sort of like making dimples in it. And so we shouldn't see like a perfect uniform brightness in that part of the sky. Instead, we should see some like really fascinating image of this star that would give us a lot of information about what was in between us and there. So Einstein thought that was an exciting observational prospect. De Sitter, who was a Dutch astronomer who was in close communication with Einstein during this period and was himself a great proponent of general relativity, wrote some papers about the observational consequences of Einstein's theory. And one of the things he pointed out is that in Einstein's model, space being finite and each straight line being closed, being a great circle, when we look at this, you know, we know where the sun is. We see one face of the sun when we look that way. If we look in exactly the opposite direction, we should see the other side of the sun. You know, much smaller, but exactly the same star. And we should be able to determine that we're looking at the same star two different ways. So those are, yeah, two interesting features of a cosmology like this. And, you know, just as quickly, people observed that you could replace Einstein's spherical spatial sections by elliptic spatial sections. So the three-dimensional analog of the elliptic plane. And then you would arrive at a model that made interestingly different predictions. In particular, it wouldn't make that thing that Einstein said about antipodal points wouldn't apply in this elliptic version of Einstein's static universe. So right away, we get some interesting ways to determine by observation whether we live in Einstein's static universe or in the elliptic version of Einstein's static universe. And so if this was a good cosmological model, we'd be able to get cool observations that would allow us to distinguish between different topologies space might have. Okay, unfortunately, it turned out it wasn't actually a good cosmological model. So I can't remember, yeah. Let's start with its first rival. So its first rival was this space-time that De Sitter constructed, also in 1917, as it was the second solution to Einstein's new equations. And De Sitter's spacetime didn't contain any matter. So its dynamics was completely dominated by the contributions of the positive cosmological constant, which acts like a repulsive force. And so space just expands under the influence of this thing. Now, De Sitter's solution was very regular. It didn't have any singularities in it. It didn't have like a Big Bang singularity or something to represent the beginning of the universe. So the only way to have something that's driven by this repulsive force and yet exists eternally in the past is to make it start out arbitrarily large, arbitrarily far in the past, contract down until it reaches a minimum, and then expand eternally in the future. And that's what De Sitter's universe does.
Professor?
Yeah.
We just have a question in the chat.
Oh, good. Good.
Would you like me to read it out?
Yeah, could you? It's actually not
Yeah.
that easy to see the chat when I'm sharing
no
the
worries.
slides.
So Jason asks, are antipodal points the same distance from each other in every direction?
Yeah, that's yes. Yeah, so just picture like the same way if we were on the sphere, an ordinary two-dimensional sphere, on the one hand, yeah, the North Pole and the South Pole, there's lots of ways of traveling along a straight line to get from the North Pole to the South Pole, and they all are exactly the same length. So just like sort of 180 degrees of whatever that is, latitude, I guess. And similarly, if you took 2 points on the equator that were opposite each other on the same sphere, it would be exactly the same story. So yeah, for each pair of antipodal points, there's all these shortest paths that are exactly the same length. And for any 2 pairs of antipodal points on a totally regular sphere, the story is exactly the same, and the distance is exactly the same between the pairs as well as within the pair. Yeah. So it's not immediate from anything I've said, but it's true that in de Sitter's spacetime, space is spherical in topology, and there's a way of dividing it up into instants of time where it's spherical in geometry as well at each instant. But the size of the sphere varies from instant to instant. They start out very big, they get smaller, and then they get bigger again. And the growth is exponential. And due to the exponential growth, a photon can never make it even halfway around de Sitter's universe. And that means that it's going to be much harder to detect global features like topology in de Sitter's universe than in Einstein's static universe, even though they both exist eternally. So that's a kind of dismaying thing. If you're, we're hoping to be able to detect cosmic topology. And there's actually, it's sort of worse than just like, oh, Einstein's thing behaves this way and de Sitter's thing behaves this way. In fact, the behavior we see in de Sitter spacetime is generic among solutions with positive cosmological constant. The Einstein behavior is very pathological and unusual. And we now think, since about 1998, that actually our own universe should look like de Sitter spacetime asymptotically towards the future because of the positive cosmological constant. So what's it say here? It's eventually noticed that Einstein's static universe is unstable. So if you change the geometry or matter content even slightly at a given time and then evolve that as initial data, what you get looks, instead of looking like something similar to the Einstein static universe at all times, instead it looks asymptotically de Sitter in at least one of the 2 temporal directions. And it turns out that typical worlds with positive cosmological constant are asymptotically de Sitter. So this exponential expansion is, it's actually very hard to avoid in the realm of the positive cosmological constant. And so our current view is that our universe is finite towards the past and doesn't look too much like de Sitter towards the past, but in the future, it will look more and more like de Sitter spacetime. So that should make it natural to worry that cosmic topology might not be empirically detectable in our universe because of this future exponential expansion and the fact that it's finite towards the past, so there's only so much we can find out about the past at any given time. And towards the future, the information is going to like race away from us before we can ever collect it. It's basically the picture. Okay, so that's another good place to pause if people have questions about any of that stuff.
I had a question. So in de Sitter's and his treatment of this, time still has a straight line topology?
Yeah. Yes. Okay. Yeah, exactly.
And so like talking about cosmic, it's both the space and the time. And so it's like trying to figure out the spaces individual.
Exactly.
Okay.
Yeah, that's exactly it. Yeah.
And then you spoke of like when you look like Einstein's like if you looked at like different changes in the temporal direction, it would look like de Sitters. What
Oh
does
yeah.
that mean?
Okay. Yeah. So what I was saying there was like, say you took, so these are, solutions to a certain set of differential equations. So often you can analyze solutions to differential equations by saying like, oh, if I make the state be this at a certain time, what does the differential equation say the history will be in the past or the future, given that initial data? And what I'm saying is, if you take Einstein's static universe, and you take the initial data and you evolve it, you get Einstein's static universe. But if you take initial data for Einstein's static universe and change it even a little bit and evolve it, what you get looks like de Sitter towards either the past or the future. So instead of staying close to, oh, hardly anything's happening, it goes wild in one direction and you get exponential expansion or exponential contraction. So yeah, this is why people say Einstein's static universe is unstable, because if you imagine perturbing it a little bit, what you get is very different from what you started with. And that's not true for de Sitter. In fact, almost everything becomes like de Sitter. De Sitter is kind of like an attractor in the space of solutions of general relativity. Did that help? I feel like I could probably do better, but
no, it made more sense. Yeah.
Okay,
Thank you.
good. Okay. Yeah, anybody else on this? Okay. So this next section is going to be the one with like too many details that probably is going to be hardest to digest. But after this, there's only 2 slides. So definitely slow me down for this section. Okay, so here's a notion of a definition of what an observationally indistinguishable pair of spacetimes. So let gamma be a world line in a general relativistic spacetime. Then the observational past of gamma is the set of points in that spacetime that can send photons to points on gamma. So that sort of makes sense. This is roughly what gamma can see, what gamma can learn about. It can learn about events that can send signals to gamma. And then we say 2 spacetimes are observationally indistinguishable if for every world line in one, there's a world line in the other one, so that their respective observational pasts have the same structure. They're isomorphic. Their matter content and their geometry both look the same. Okay, so that's a kind of natural definition. Here are some quick consequences of it. Minkowski spacetime is only observationally indistinguishable from itself, because in Minkowski spacetime, if you have a world line that goes on forever, it can eventually see every point in the past, right? Because there's nothing to stop you from sending a signal from any point that will eventually reach gamma. And similarly, the Einstein static universe is observationally indistinguishable only from itself. I mean, in fact, because space isn't expanding or anything, it doesn't even take that long for photons to explore all of space and come back to you. So yeah, if you're an observer in Einstein static universe, eventually you'll know everything that ever happens. But, and this is the thing we'll be interested in the next few slides, there are Big Bang style spacetimes that start with singularities and then expand, that are observationally indistinguishable from one another, even though they have different spatial topologies. So we'll show how to construct a pair of spacetimes that are Big Bang spacetimes that have different spatial topologies and that are observationally indistinguishable from one another. So that's telling you, I can't figure out what the topology of space is by performing observations, even if I live forever and I have perfect instruments. So in that sense, we cannot learn the shape of space. It's giving away the punchline for this. I'm going to skip the last bullet point, even though I like it the best. Okay, so let's talk about cosmological spacetimes in general relativity. So from where we sit in our universe, at cosmological scales, the universe looks much the same in every direction. Right? So obviously the night sky has all kinds of interesting structure in it. But if you sort of blur it out and look at it at the biggest scales, it doesn't have that much structure anymore. It's basically the same in every direction. That's a super interesting fact about the night sky. So if we assume that where we sit isn't special, we should think, okay, we live in a universe where you can find observers who see the night sky looking the same in every direction. A whole family of observers that sort of fill up all of space-time. And that forces what's going on in each spatial slice to be both homogeneous, the same at each point, and isotropic, the same in each spatial direction. Okay, it's not that surprising that if you force space to be homogeneous and isotropic, then you're also forcing it to have constant curvature, right? Because if it's the same at each point, this K thing must look the same at each point. And if it's the same in each direction, K must also look the same on each plane. So basically by saying we want cosmological models in which there are special observers who see the night sky being isotropic, the same in every direction, we're saying we want a model in which the spatial geometry has constant curvature. So you specify such a model basically by saying, I want the constant curvature to be negative, 0, or positive. Pick a topology for space that's consistent with that constant curvature. And then you just need one dynamical variable, which is a scale factor that tells you basically about the expansion or contraction of space. So you sort of fix this topological information, and then you fix the scale factor, and now you've completely described the geometry of a Big Bang style. It's even more general than Big Bang, sorry, of a isotropic cosmology. Now, the actual behavior of A of t will depend on initial conditions and also on the matter content of space-time. But typically, in cosmology, at least to build the basic models, you don't worry so much about matter. You make it really simple. So you make it something like some massive matter and a radiation fluid and the positive cosmological constant, and that's it. So we can actually say quite a bit about what observation forces on us once we've taken those steps we made on the preceding slide. Observation heavily favors saying that the constant curvature of the geometry of space is 0, that space is flat, that the time variable goes from 0 to infinity. So it's, the actual, where you put the origin doesn't matter, but it's finite towards the past and infinite towards the future. And for small values of t, the scale factor looks like square root of t, and for large values of t, it looks like an exponential function. That last thing, that for large values of t, it looks like an exponential function, basically just follows from saying there's a positive cosmological constant. The asymptotics towards the past depends a little bit on the details of the matter content, but this is basically all we need to know about it. So in a space-time like this, there'll be fundamental observers who see the sky looking the same in each direction. So let's consider some particular fundamental observer who has that feature, like attached to the Earth, say. And just suppose all the other observers in this universe are constantly, frantically trying to signal gamma 0. At any time t, we can cut out a spatial slice t and look at, within that spatial slice, all the observers who ever have or ever will manage to get their signal to gamma 0. And that will, those observers will form a finite ball around gamma 0. Okay, so it's definitely not true in a universe like this because of the exponential expansion towards the past, towards the future, that signals from arbitrarily far away, sent arbitrarily early, will ever get to gamma 0. And you can sort of see why in this diagram at the bottom of the page. unfortunately, I don't know why people do this. The time direction is horizontal in this diagram. And at each point, there's kind of a representation of the future light cone. And you can see as you go along a horizontal line, the future light cones start out really wide. That's because of the square root of t behavior towards the past. But then they get really, really narrow as you go towards the right. That's because of the exponential expansion of space. And you can sort of see like that sort of double line there is a typical photon that somebody's trying to send. And it's never going to travel further up the page than that dotted horizontal line. It's never going to, and a signal sent the other direction would never travel further down the page than that other dotted horizontal line. That's just telling you you can't send a signal from the point that that photon originates to some fundamental observer represented by a horizontal line that's far away on the page. And this is just a fact of life about behavior of photons in universes with positive cosmological constants, unless you do something really tricky like Einstein did to make his very exceptional universe. Okay, so now we're almost there to how we can, starting from the universe that we've been talking about on the last two slides, we can make a new cosmological model, observationally indistinguishable from it, and with a different spatial topology. So here's how we do it. We start with the thing we were just talking about. So a spatially Euclidean cosmological model. We choose a fundamental observer. On each time slice, we make that sphere that I was just talking about, the sphere that contains the observers who ever have or ever will manage to send a signal to gamma 0 and excludes all the other observers. We take that sphere and we build a cube that's large enough to contain it on each slice. And then within each slice, we throw away everything outside that cube. We delete everything outside that cube. And then we identify opposite faces of the cube, just like we were doing to build the torus in 2 dimensions at the beginning of the talk. And the resulting thing will be a Big Bang style spacetime that is finite towards the past, expands exponentially towards the future, has flat spatial slices, but now they're toruses instead of all of Euclidean space, 3 toruses. And because in the Euclidean thing we started with, observers could only see so far anyway, nobody's ever going to be able to see enough in this new spatially toroidal space-time to find out that they're living in something that's spatially finite instead of spatially infinite. So what we get will satisfy, we just made a pair of solutions, a pair of cosmologies, and they satisfy the official definition of observationally indistinguishable spacetimes. So observation can't determine cosmic topology in worlds like ours if these are the right kinds of models to use, even if we imagine that observers live forever and have perfect instruments. So in these models, observation underdetermines topology. The class of models observationally indistinguishable from our basic spatially Euclidean Big Bang model features 18 different spatial topologies. So for all we can tell, people tend to work with the spatially Euclidean one because it's the easiest, but there's 17 other options for the topology of space. Okay, but here's another way of looking at it. To the extent that observation has singled out this class of models, it has almost determined spatial topology because there's infinitely many possible spatial topologies in general relativity, and observation has cut us down to this family that just has 18 spatial topologies in it. So we went from infinitely many to 18. That's really, really close to fully determining the topology of space. Okay, so I think I could either stop there or do one more slide that has that tells you something surprising. But let me pause for questions and see. Maybe by saying the next slide is the exciting one, I've already pressurized people. So let me just say what's on the next slide. So what's on the next slide is basically this. So those results I was just talking about were things people knew in the 1970s. They started to seem a lot more interesting when we found out that there was a positive cosmological constant. But this stuff on this slide is something that was established like only in the last 7 or 8 years, I think. This guy Ringström, a mathematician, he introduced a notion of indistinguishability that's weaker than the one we were working with. So first of all, because it requires only approximate agreement between the two solutions. It doesn't require a perfect match like what we were working with. But also because he focuses only on a portion of the space-time. So in a Big Bang style cosmology, there's an early period right after the Big Bang when the universe is not transparent to photons. It's too hot for photons to travel very far. Eventually it cools, and there's this sudden moment when you start to form atoms that are stable, and also photons start to range freely. And one of Ringström's thoughts is, okay, let's, when we talk about what an observer can see, we should talk about everything in the past of the observer and to the future of that freezing out moment when photons first start to move freely. Okay, so that's the first bullet point. Second bullet point. We'll say that two cosmological models are approximately observationally indistinguishable if for any observer in one, we can find an observer in the other, so that the portions of their respective spacetimes accessible to these observers are approximately isomorphic. Okay, so it's like the original definition, but now we make those two changes I was talking about in the first bullet point. And then the amazing thing that Ringström showed is that given any Euclidean Big Bang model and any closed spatial topology, not just one of the special ones that's consistent with a flat geometry, there's a cosmological model with that spatial topology that's approximately observationally indistinguishable from M. So Ringström has given us a sense in which observation dramatically fails to determine spatial topology. It leaves open every possibility for what spatial topology could be, given the kind of universe we live in: finite towards the past, hot Big Bang, exponential expansion towards the future. So no, we can't know the shape of space. We can't know anything about it, in fact. Okay. I think I should just stop there. So I have one other thing, but let me just stop and say thanks. At the beginning, I started with that quote from Peirce, sort of espousing this like incredible optimism that science could settle every question if you just gave it enough data. And of course, even in the 19th century, people were incredulous about that and gave him all sorts of guff about it. And he eventually wrote this thing where he said, look, it's very hard. People, it seems like right now, as Peirce is writing in this other thing was written in 1898, it seems like there's all these questions that we'll never be able to settle. But you'd be foolish to go out on a limb about that, because just think about how in the 1830s, when you pressed people to say what we could never learn, they gave as an example what stars are made of. And then like almost as soon as people said that, the spectroscope was invented and it became possible to find out what stars are made of chemically. And so Peirce is thinking like, yeah, there's lots of things we can't find out right now, but you'd be foolish to say we'll never be able to find them out. And then there's this weird sentence at the end of the passage where he says, yeah, it would be as dangerous as the voyage of André. André with 2 E's on the end. And I liked the rest of the thing, but I wanted to figure out what the voyage of André was. So I looked it up, and it was a 19th century polar expedition. So this guy André and 2 other guys were supposed to take a balloon from an island that belongs to Norway to the North Pole. But after flying along for 2 days, the balloon crashed. And then there's a sort of tragic end to the story where they never managed to get back. They were never rescued. For a long time, it was a mystery where they were. Like Peirce was writing while they were still missing. And it took like 35 years before they eventually found the bodies and the balloon and so on. And they also found all these undeveloped photographic negatives So it turns out these guys, after their balloon crashed, took a lot of amazing pictures of the Arctic, including this one of their destroyed balloon. So it's really got nothing to do with the talk, except Peirce mentioned it, and I got excited when I figured out what it was.